So thanks for the introduction, Alexander. As you have told, I want to start and talk about today about model-based automation and verification in the area of automotive SOC development. And therefore, I want to give you a short introduction in the world of SOCs. We have now talked a little bit about SOCs, but I want to give you a short background talking about verification and the challenges in SOC development and verification we see today, and then show our approach and the case study we have done as part of the work to address these challenges. And at the end, I give you a short conclusion. So here you can see a typical car with such a control unit, and all of this control unit consists of minimal of one system in package, I think, and the system in package often consists of such a sensor and MEMS and microsensor and our SOC. And this SOC has an analog hardware part, maybe a digital non-programmable hardware part, and a processor. Here, I want to show a little bit generalized block diagram of such an SOC. So we have the external interfaces for data buses like CAN or SPI. On the orange block here means or represents the signal path oriented parts. The blue blocks is we call them control flow oriented parts like general purpose processor, GPP, and RAM and ROM, and such more. But these are the focus today we want to talk about. And at the end, we need some buses and bridges to connect all these parts together. Verification gets more and more complex and gets more and more important, I think. And up to 50% today of the project resources are needed to do the verification. And more than 50% of these verified designs are consisting of functional errors, and thus so they need to necessary rework and the additional effort and costs. One result of these 2 points is, I think, the gap of productivity we have today. So this means we try to illustrate it here on the left side. We have an increase of the complexity. So the transistor density is one indicator for the complexity of our SOCs, but also of other embedded systems, I think. But we only enable to increase our productivity per year by almost 20%. So the bigger increase at the end is only because of reuse of other versions or of older versions, I want to say. So now I want to talk about the definition of verification. I think all of us knows what verification is in principle because we are on the DVCon. But if we take a more detailed look about the definition, we find some obstacles here. So the verification proves that a system has been correctly designed with respect to its specification. This means we are able to detect design errors. So if the implementation is wrong in the respect to the specification, it'd be easy to find this with our verification. But we get a problem if the specification is wrong. So if the specification is maybe ambiguous or incomplete, then we get maybe errors in our design too, but we are not able to verify this. And the bigger point is we get not considered scenarios in our verification. And by this, it could be happen that we get unpredictable states of our system, of our SOC, or our control unit overall at the customer side. And this is really risky, especially in the area of automotive SOC. So this are really a risk of human life, I think. So this means the specification is really important and have a direct impact to the quality of our verification. Because of this, we thought about how the specification flow looks like in our SOC development in the moment. And we start with the product requirement specification from the customers and develop the function specification, sometimes with the customer together, sometimes at our own. And parallel to this, we start to develop the system concept, which means a really abstract version of our system and first idea of the system with some informations, but not too detailed. In this work, we get some requirements, some system requirements on our own system, and this will be described in the concept specification. But if we switch from the concept phase to the design phase, we call this, we need more detailed information. So we want to implement our system, so we need more and more detailed information about the implementation, about the modules, about the connectivities, and we all have to describe this in the design specification and have to be sure that the system design, the implemented system design and design specification is consistent. More or less at the end, we have, for example, we have very important the verification, and we want to show you here a little bit more detail. So in our case, we need a verification plan, maybe, or definitely some assertions to check our implementation, and maybe a reference model. And now I want to show some obstacles we detected here. At first, the most of these documents and descriptions are done in natural language, and natural language is not only error-prone, it's really interpretable. So we can't be sure in the moment that maybe the customers understand the same described informations differently to our engineer, or the architect understands it differently to our module designer. And this is really error-prone, and it leads to big mistakes in our development. The second point is we have many steps of manual transfer between these different description languages. So,
Alyosha, we can't hear you anymore. Not sure whether you hear me, just in case. We can't hear you anymore.
Can you tell me where to stop it? Because I don't know what minute should I stop in.
at the end, this is a little bit an add-on point. So, because it's really important, if
Is it here? Or should I skip more?
Please all mute your mics.
Sorry. Should I skip it more or play from here?
Okay, sorry, you are the second technician. Yeah, here it's fine. You can continue from here, I think. That's where he was, I think.
Okay.
get an incomplete specification, the incomplete verification is really risky. So we have to think about it. So how we want to address this? At first, we want to think to get a better quality of our specification, and therefore we enabled a model-based and formalized specification. So we use SysML as modeling language for our specification. And we further formalize SysML. We use only a subset and define really strange which model element describes which component, for example, or which module or which aspect of our SOC. So this is really important for us, and therefore we can reduce the interpretations in our
So Alyosha is back.
Second point is we have developed a model-based development or specification methodology, and by this we want to reduce the inconsistency. We want to increase the traceability, and we think we are able to get a complete specification or a completer specification. And I'm sure if it's possible, we are able.
Okay, switching back. Sorry for the hiccups. I think we need to promote Alyosha again. CC16, can you please promote? Oh, perfect. Thank you very much. And Alyosha, you should now be able to share again and unmute yourself.
Big sorry.
No problem. This happens when you go for virtual conferences, you can never fully avoid.
So now I hope you can see again.
Yes, all good.
Okay. So I think I'll start again with this slide. Sorry. So how we want to address these obstacles we have detected at first, we want to, or we had enabled or developed a methodology for formalization and modeling the specification by SysML. So this means not we use only SysML, so we have a real additional formalization how we want to use SysML in the context of SOC. Furthermore, we want to, or we had to develop a methodology for model-based development and specification in the area of SOC. By this, we want to get a system concept what is developed in the model, in the SysML model, and not only as an informal collection. Sorry. And we want to reduce the inconsistency and the missing traceability. And we think by using a methodology for the specification, model-based methodology, we get a more complete specification, and by this, a better verification. And by the formalization and modeling of our specification, we get a more machine-readable standard, and this enables the generation. And in this work here, in the context of this presentation, we means the generation for verification. So as you remember the picture before, we here adapt our specification flow a little bit with our new approaches. So at first we need a modeling method over the whole flow, but what we need is, or what we want to enable is a system concept fully complete modeled in SysML. This is the starting point, but we recognize really soon that it makes not sense to model all information of our concept and all information of our SOC. So we decide to divide these informations. We have a concept specification in natural language, and we have our system concept, which is modeled with the whole, or with mostly the whole informations we need in the model. And what we done now is we have a real strong linking between these artifacts in the natural language description, and the artifacts in our model by bidirectional linking. If we switch from the concept phase to design phase, our working flow changing a little bit. So here we try to enable a specification consisting of natural language and model, and these both databases, and these are different tools which are strongly connected together, enable a specification consisting of two different databases. And as I told you, we get by this a better traceability. We get a machine-readable format, and this enables at first the generation maybe for implementation stuff, but also it enables the generation for our verification. Now I want to talk a little bit more about our flow, our new flow, our methodology for the model-based development. And for this, we have divided this really big model, and we get always a big model if we want to model a SOC into three submodels. At first, we have the system context model. There we have to describe already known the use cases, but also we want to think about what technical context we have. So our SOC is always a part of a bigger system, and it's really important to think at the beginning what interfaces we need, what are the system around us. So in the next step, we go to the functional model, and there we model for each use case. We get a high-level functionality, or we call them external functionality, and we make a decomposition and think about what internal functionalities we really need. And what we also can do here, we can use activity diagrams or other behavior diagrams of the SysML world to show the relationships between these functionalities. What is really important for us is to enable here and more a top-down approach. So think first what functionality you really need, and then think about the realization, because in the moment we have a big amount of reuse, and our architects have an working flow, so they want to always to reuse their informations, to reuse maybe some modules, and then we get often and realized functionalities what is never requested by our customer. So, and in the last step, more or less the last step, we start with thinking what modules we need for maybe which functionalities we have to realize with software, which we have to realize with hardware, and which hardware modules we need. This is here realized in the block definition diagram. And what we additionally do is here, we use the internal block diagram to model our architecture. And how it looks like, I want to show you here in a really easy example. On the left side, we have the block definition diagram. Here we use blocks to model only the hierarchical representation of our system. And on the right side, we have the real architecture. And here we use parts. These are SysML modeling elements. And the special thing here is that these blocks and these parts are one thing. So these can be understood a little bit like classes and instances. And so they are really strong connected between the diagram versions. So now I have to show you how we can model our architecture, and now we want to enable and use of this information we have already described very detailed sometimes in our model. And this is our second step. So we enabled a generation of assertions for connectivity checks out of the architecture model. For this, we need a two-step generation. In the first step, we need a scripting which detect for each starting port and end port over the whole hierarchy of our SOC and write it to the CSV table. And in the second step, this Python script we have written read out this information and write the connectivity checks for us. So to show you a more practical example, we use a subsystem of one of our SOCs. And this is here, again, a little bit generalized, but what we use is a subsystem what is a part of the control flow oriented part. So it's in this area we work normally. And the main functionalities of the subsystem is to store and load initial values for the boot loading with the one-time programmable and do some redundancy check. But the functionality and the details about the subsystem is not too important today. So how it looks like in our model. Here you can see the block definition diagram. We now call them hierarchical technical diagram. This naming is part of our formalization. And as you can see here very well, the architectural hierarchy of our system, we have modules and submodules, and we used here such a color scheme only for this presentation to show a little bit more the hierarchy. The next step is to model the architecture in the block definition, in the internal block diagram, sorry. And as you can see here, again, the same color scheme. But what you also can see here is the additional details comparing to the block definition diagram. And we've shown here the connections between the submodules. And what you also can see here, we have often connection. They goes over different hierarchy levels and have ports beside the start and the end port. And this is a little bit tricky for our scripting. So here on the left side, you see in part of our picture I've seen before, and we want to show more detailed about the connection CRC enable from the rec module or submodule to the CRC FSM submodule. And as you can see, for each of these connections, we get one assertions. And the assertions only check if the port of this module is connected with the port of the other module. And if it is not, then please throw an error. What you also can see here, we have a second task to do with our scripting. We have a SysML naming convention. We want to fulfill in our modeling the specification, but we have also a naming convention from the VHDL side because our assertion checks the connectivity in the VHDL architecture. So the scripting have to change the naming convention. Here we have the its rec, for example, and in our assertion, it have to be called rec and I, for instance. If we have generated our assertions, we load it to the OneSpin, our verification tool we use in the moment, and run it together with our VHDL architecture we have written by hand, so manually. And in the first step, we load there an fully correct VHDL architecture and check if our assertions are hold and pass, and this is the case. And in the second step, we load an architecture with a missing connection, with two missing connections. And again, we check if our assertions throw an error for this connection and it also works. So at the end, I want to give you a short conclusion. So what are our results? We developed a methodology for a top-down and model-based development in the area of SOCs. We get a method for formalization and modeling the specification. And by this, we are able to increase the completeness, the understanding, so the easier to understand and the uniqueness of our specification. We enable the generation of assertions for connectivity checks. And we are able to do a case study with an industrial example to show that it really works in a productive way. By this, we enable a reduction of bugs and rework. And then a reduction of bugs is not only in the implementation, and we are also enable a reduction of problems in our specification. We are able to reduce problems in our verification because our specification is more unique. We are increasing the verification coverage, so we don't want to have some not considered scenarios. This is really important for us, and if you have a complete specification or more complete specification, then we can enable an increase of the verification coverage. We reduce the effort, not only by the automation, also our specification, we get the response that it is easier to understand for the verification engineer, and so it's really easier to get his verification planned. And the last point, it's really a big point, I think, by our specification methodology, we have a directly impact for the verification, and we have further potential for generation automation. For example, we think about we are enabled to generate system C reference models directly out of our model. And this is, I think, the biggest benefit of all the work, because the modeling is a big additional effort, and we have to think about how we can get some better or some further potential to reduce the effort overall. Yeah, this was my presentation. I thank you for your attention. I hope you have some questions for me.
Alyosha, thank you very much for the presentation. From the discussion in the chat, I sense that there will be some questions. So first question is from Irek Subansky. How do you validate the model? Can you simulate it? Can you formally verify it?
We worked on it. So the first step is we simulated what is possible to simulate. So if we have a real big model and we have some parts of the model are not simulated, because the point is, if you want to simulate it, then you have to have it real complete you have to describe everything, and this is not possible on all stages of our development flow. I think at the end we have to simulate. Yeah, but the validation is, I think, more or less the same like in a validation indoors or another natural description. We have to read it and we have to try to understand it. So we need a validation for sure.
Okay, thanks. Mitsuhashi Akio asks, do you have any plan to extend model-based approach to test bench test scenario areas such as portable stimulus?
Yeah, we hope we are able to do it in the future. We think about it in the moment, but so for us, it's because it's a real big work, and we also work on how we can specify it, and how for us is always the question how we can develop a flow, an overall flow, which are get acceptance at the engineer side. And the problem at all is we are able to generate more and more things, but for this we also have to model it, and we have to be sure that the model effort is not getting not too big to enable a generation at the end. But we want to test and check if we can do more generation in the kind of test benches. Yes.
Thank you. Gabriel Pakiana asks, how traceability is implemented from requirements to the architecture? Is there a bidirectional link?
Yes. What we do is we use the Ration Rhapsody toolchain or Rhapsody toolchain. So we have Doors Next Gen on the one side. So we have everything on the server driven solution, and we connect really bidirectional linking between the Doors description. So this is the natural language part and the model. So the first step in our case is we want to reduce, or we want to delete and to model all this.
Okay, now he dropped again, I believe. Maybe people who want to stay, maybe let's give a few more moments for him to come back. I used the interruption to remind once more, please join us in the 3D world, and also please do the best paper voting. Hats off to the moderator. Thank you. if that's meant to go to me.
Sorry again.
No
always
problem.
My tab is. I don't know what happens here.
Yeah, welcome back.
Yeah, thanks a lot.
We waited for you. So we were at the question, how traceability is implemented from requirements to the architecture. Is there a bidirectional link?
Yeah, correct. So I see here from Walter Thibault, the second question, what means bidirectional linking? And this means, so it's possible to do the linking from the artifacts in our door specification. So this means the natural language description to the artifacts in our model and the other way around. And what is possible is we are able to jump from the one tool directly to the diagram, for example, and the other way around. And if we change something on the, for example, at the model, and we have a linking to our requirements indoors, then we get there a hint and then a hint there is something changed. Please check the connectivity. And so this is mean with bi-directional linking, I want to say. I hope this answered the question more or less. It's really tool special because of this. Don't want to talk too much about it in my presentation, but maybe we can discuss it later in the virtual room.
Sure.
More detailed.
There was one more question from Walter also. I'm not sure whether you kind of answered that implicitly. How do you deal with that the hierarchy and concept can differ with the actual design?
So normally it shouldn't. So normally, yeah, it can be there is some inconsistency, but our main target is to generate the implementation out of our models, and then we hope we can get more or less and fully consistency between the implementation and the specification. This is more or less a trimming for the future. In the moment, it's clear we can't be sure that there is some inconsistency, but we think by the top-down approach and the modeling approach, it's easier to detect inconsistencies and to prevent it. So, yeah.
Right. Good. Thank you very much. There are no more questions in the feed. So if one more question coming, so I think we can allow for that, and then we go to the break. Ons Membarek asks, do you IP exact along with your SysML based modeling and assertion generation based flow?
Yes. We worked on it, so we are at the starting point in the moment, I have to say. But what we can do is we use IP exec description to generate connectivity or not connectivity. So in SysML we have ports, and these ports have to be the naming, or we need the naming from IP exec. So our IP exec is the second starting point for the register description. And what we try to enable is an generation from IP exec to SysML to get the namings there and to use the namings in SysML model for register description from IP exec. So this is a good example. So it makes no sense to describe the registers in SysML because IP exec is more comfortable for this description. But we have to be sure that there is a consistency between these both.
Thank you. Mitsuhashi Akio writes in the feed, thank you, Alyosha, great session. I can only second that. And with that, I would like to close the session. Please join us in the virtual world. Please vote for best paper. And please also do not forget to visit the posters. Thank you very much for joining the sessions. We had close to 50 people in the session at max. Thanks also to CC16 for technically managing the session, and thanks to the presenters. And yeah, see you around later. Enjoy your break. We'll meet in the 3D world. Cheers. Bye.